Hello everyone and welcome to my presentation on towards orchestration of cloud edge architectures with Kubernetes. The motivation for our work is cloud edge orchestration. So first of all, what is edge computing about? In edge computing, we are trying to provide computational and storage resources in close proximity to mobile devices, sensors, end users and IoT. And we do that to achieve a better latency, because the applications are in close proximity to the requesting devices, for better scalability, because then cloud and edge nodes are available to scale out applications, and also for privacy, because not all of the data is transmitted to the cloud. Of course, edge computing provides some challenges, so the deployment is a quite complicated task because we need to achieve a resource-efficient deployment of the cloud as well as the edge layer. The management is a bit more difficult because we need to manage a lot of devices, for example, in the edge layer, and also scaling might be quite complicated because we need to scale out applications in the cloud layer as well as in the edge layer. This is covered basically by cloud edge orchestration. So cloud edge orchestration tries to answer the question when, where and how to shift computational resources, as we can see here in this first figure at the bottom of the slide. So there are a couple of cloud and edge nodes, and the cloud nodes and the edge nodes are downloading containerized applications from a central container registry, and there are different so-called provision models between cloud and edge. So we could scale the application, that means the application is running in the cloud as well as in the edge layer. We can offload the application, that means the application is running in the cloud and then shifted to the edge layer because of latency requirements, and it's not running in the cloud anymore. And the third option would be edge-only deployments, so a set of applications is only executed in the edge layer. And all of these provision models, all of these actions are managed by our autonomic controller, and this autonomic controller consists of a central orchestrator, and this orchestrator is implementing a certain strategy, algorithm or policy in order to decide when, where and how to scale, offload or provide edge-only deployments. The difficult question here is how can dynamic allocation of applications on cloud and edge nodes over time be achieved, and this should be done based on the real-time resource utilization, the end user's perceived latency, and of course the bandwidth. Over the years, many cloud edge orchestrators have emerged, and KLS can be seen as the state-of-the-art container orchestration platform, mainly for cloud environments. It provides high availability, scalability and fault-tolerant clusters from containerized deployments, and these properties can be seen as essential for edge computing, respectively edge orchestration. Kubernetes allows us to extend or override the default and cloud optimized components and their behavior as well. So for example, we might override the behavior of the kube scheduler, and also we might introduce further components which can be used by Kubernetes. This leads us to the outline of our research. So for our objectives, we want to investigate the state-of-the-art KLS-based cloud edge architectures, as well as KLS as single, uniform and easy to use orchestration platform. This leads us to the following research questions and methodology. So in the first step, we want to examine the general requirements of edge orchestrations, and we will analyze, based on this requirement, the coverage and shortcomings of Kubernetes. And in the second step, we will analyze the benefits and drawbacks of KLS-based cloud edge architectures in regards to the general requirements of edge orchestration. In a third step, we want to assess the solvability of shortcomings and drawbacks of Kubernetes as well as the KLS-based cloud edge architectures. Of course, compliant to the general requirements of edge orchestration and the design principles of Kubernetes to finally assess the feasibility of K8s as cloud edge orchestration platform for complex edge orchestration. We will do that by performing a structured literature review, and finally 11 papers were part of our study. To answer our first research questions, we will talk here about the resource-related requirements in cloud edge orchestrations, and what we can see here is a generic Kubernetes cluster annotated with several scenarios which might be difficult for cloud edge orchestrations. So in the first step, Kubernetes is performing static resource-based scheduling for new containers, which should be scheduled on a set of worker nodes, and Kubernetes is doing that based on CPU and memory resources. However, real-time utilization, real-time energy consumption, the end user's perceived and desired latency and bandwidth is desired for cloud edge orchestration and edge computing. So as we can see here in the first example, so there's a container with a static resource requirement which can be defined by the developer, and Kubernetes is scheduling this containerized applications based on a set of rules, of predicates and priorities to the next worker node without regarding the current real-time utilization of a particular worker node. And this might be problematic in edge architectures. As second point, the scaling as well as the scheduling is only based on CPU and memory utilization, so no other important metrics like latency and bandwidth are considered here. So basically the same problem. So the horizontal pod auto scheduler is in charge of scaling out a containerized application, as we can see here in the second example. So based on the available resources and the current real-time CPU memory utilization, Kubernetes is scaling out the containerized application. As a third point, might be a problem for multi-container applications. So let's assume we do have a more complicated application consisting of 3 containers, and the 3 containers are interacting with each other, and based on the available resources, the multi-container application might be separated and the single containers are scheduled to different worker nodes, and this might have implications on the performance. The fourth problem is that Kubernetes is assuming that all nodes are homogeneous, but usually in edge computing we are dealing with heterogeneous edge nodes. And as the last problem for resource-related limitations of Kubernetes, the K8s-related components which must run on the different worker nodes may mitigate the performance. So as you can see here, each node is running the K-proxy and the kubelets, and this might have implications especially for low-end devices. Regarding our second category, the architecture-related limitations of edge orchestration, the first one would be that the potentially high available control plane violates, well, the desired decentralized architecture in edge computing. So as you can see here on the left side, it is possible to replicate the control plane in order to achieve high availability. However, it is still a centralized architecture. As seventh limitations, a single Kubernetes cluster, as we can see it here on this slide, is limited to 5,000 nodes, 150,000 pods and 300,000 containers. This is quite a lot, but for complex and large-scale cloud edge architectures, which may be larger, this could be a limitation. And as last but not least, Kubernetes does not use a particular network topology. That means there is no awareness of K8S if nodes are either cloud or edge nodes. However, for all of these limitations, for the resource and architecture related limitations, there are potential solutions. So starting at the requirement for real-time metrics, we could implement a custom metric server. So to use real-time CPU, memory, latency, bandwidth and jitter metrics, and these custom metric server can forward all the collected metrics to the Kubernetes scheduler and the horizontal pod autoscaler, which are in charge of calculating new deployments and to perform scale outs. And also for the custom scheduling and scaling mechanism, we can introduce adjusted recompiled, native or extended schedulers. And these schedulers or scalers can run instead of or alongside the default scheduler. So this might solve the first 4 problems. Regarding the low-end devices that Kubernetes may not run on real low-end devices, we can use Lightweight Kubernetes, which provides a resource optimized version of Kubernetes. For example, micro K8S or K3S might be a good solution for this problem. Regarding the architecture related side, the centralization can be seen as a neglectable aspect here because of already established cloud edge architectures which are using a centralized architecture anyway. For our limitations of nodes and pods and containers, we can use multiple clusters, and for example we may connect these clusters by cluster federations. And as last but not least, the missing topology of Kubernetes. And here what we have also obtained in our studies, labels were assigned to the nodes in order to introduce a particular topology. We separated the requirements of cloud edge orchestration in resource related and architecture related requirements, and now we can have a look at the limitations or the proposed solutions in a resource related way to answer research question 2. We found what is quite well supported, the support of edge layers, so most of the solutions focused on efficient orchestration of the edge layer, and also the introduction of custom schedulers. So most of the solution introduced an additional scheduler component in order to achieve the desired scheduling and scaling behavior. What was moderately supported, the simultaneous support of cloud edge layers, so only a few solutions considered the simultaneous orchestration of cloud and the edge with the same architecture, and also the custom metrics, so only a few solutions introduced custom metric server to provide a real-time resource metrics, for example. Poorly supported were recompiled, native and extended schedulers, and also the dynamic real-time scheduling of resources. So most of the solutions didn't use real-time CPU memory, disk or energy related metrics in order to calculate new efficient deployments. And finally, the real-time bandwidth, which might be quite important for latency-aware deployments, were poorly covered. Regarding the architectural related requirements, we can conclude that the limitations of the proposed solutions are as follows. So quite well supported is the edge topology, so labels were assigned to a set of worker nodes in order to make Kubernetes aware of the different layers, and also edge-only deployments, because most of the solutions focus only on edge-only deployments, respectively were able to perform edge-only deployments as provision model. Moderately supported was the cloud edge topology, so only in a few cases nodes were tagged as cloud or edge nodes, and also the implicit offloading. So most of the solutions provided a way of offloading, but not in an explicit way, only implicitly. Poorly supported was scaling as well as explicit offloading. There's no real way to offload an application from the cloud to the edge. Also poorly supported was the cluster-wide fault tolerance, which is a quite essential requirement in edge computing, because often we are working in critical areas like smart traffic control system, and this would be really desirable to implement. And finally, replicated container registry were also a major issue. After the limitations of the proposed solutions, we can sum up our findings and answer the research questions again. So for the first research questions, what are the requirements of edge orchestration? We introduced two categories. First of all, resource-related requirements with consideration of the different layers, so which layers are targeted, then real-time resource utilization, the network awareness, and also the metrics which can be used for the cloud edge orchestration, and also the architectural requirements. What was covered by KLS, the basic scheduling based on CPU memory resources, fault tolerance, and also security mechanisms, because all the traffic between the cloud and the edge regarding the control plane related communication is encrypted by default. The shortcomings of KLS are the heterogeneous structure and also the missing capability of handling dynamic real-time resource utilization. Regarding our second research questions, what are the benefits and shortcomings of KLS-based cloud edge architectures? So the benefits are the real-time resource utilization, the implementation of custom schedulers, introduction of the usage of metric components, and the implementation of the network topology. And the shortcomings were the missing support for different provision models, then the not well implemented fault tolerance, and the missing usage of geo-replicated container registries. Finally, to our third research question, how can we assess the solvability? And in our opinion, the shortcomings and downsides are solvable with a foreseeable effort, because KLS and its modular design allows us to replace and customize components, and also the shortcomings of the implementation should be solvable, for example by replicating deployments, control planes, and also the usage of geo-replicated container registries. Regarding the limitations and the future work, our study is limited to some extent because of simplification. Our use criteria catalog might not cover all of the requirements of edge computing and edge orchestration, and also the comparability is still to question, because the investigated KLS-based cloud edge architectures might target different approaches and objectives, for example, centralization versus decentralized approaches. Also regarding the scope, supporting all provision models and deployment to the different edge technologies may be out of scope, and we found out that edge only is the most frequent provision model which was used by the different architectures. However, we believe that mission-critical requirements of edge computing must not be compromised by the different implementation approaches. We plan to use KLS as a single uniform and easy-to-use orchestration platform for complex cloud edge orchestration, and we want to do that by providing architectural blueprints to set up mission-critical KLS-based cloud edge architectures. And finally, we want to make available already established generic cloud edge orchestration algorithms as native scheduler package in KLS, fostering the standardization and the wide usage of these already established cloud edge orchestration algorithms in edge computing via KLS. Thank you very much for your attention.